this is 5-9 notes, and we're doing operations with complex numbers. So recall that a complex number has a real part and imaginary. So A is the real, BI is the imaginary part. And what does I represent? Square root of -1. Okay, now I have this first problem here. It says adding, subtracting complex numbers is very similar to adding, subtracting variable expressions. There's no equal sign here. So when we go to add like terms, we're basically looking, and they rearranged it. So the 9y would be paired with the -2y. Do you see how they paired that up? 7y. And then the -4x gets paired with the -3x. So here they paired it. There's my -7x. And then the constants get paired up, and we get our -2. So you're going to treat I like a variable. And if you have something with I, you're going to add it or subtract it just like you would and keep the like term. Before we get into that addition and subtraction, just to remind you, they use the commutative property by rearranging the problem. And if you want to see the associative property in action, we would then group and say, hey, add these two, plus we added these two, and then we added these two. So I'm not changing anything. The commutative property rearranges the numbers, and the associative property lets us group them and say, add these first, add these, and then these, and here it is. Distributive property, same deal, distribute that A. All of these properties work with I. Okay, so you're going to treat I like a variable, but I represents the square root of -1. Now, we also want to talk about higher powers on I. So this is the harder part today, and then it will be a little bit easier when we do our operations. When we have I, we already know that equals the square root of -1. And we never leave the square root of -1. We always make it an I. Do you remember what I squared equaled? I did bring it up. What is it? It's -1. Okay. I squared is the same as I times I. Do we agree with it? Like, let's derive this and find out where this came from. And if you take I times I, isn't that the same as square root of -1 times the square root of -1? Isn't that the same as the square root of -1 squared? I mean, I could have skipped all this. I squared is the same as the square root of -1 squared. And what happens when we square square root? And we get -1. So it's the idea that we can sort of break this down. But I do need you to know these two facts. When you see I, it came from the square root of -1. And when you see I squared, we know it is -1. These two things have to be in your memory bank. Got it? I can always figure out what I squared is by thinking about I squared being the square root of -1 squared, and it stays -1. So what is I to the third? Well, let's break it down to what we know. Can't I use my power properties and write this as I squared times I? I know that doesn't look like an I squared because my pen, but isn't that the same idea there? So what does I squared equal? -1. And what is I? I. So I to the third is -I. So anytime I'm giving a higher power, I'm going to use my power properties that when I multiply bases, I add the powers, and I'm always going to break it down to an I or an I squared. So if you look at I to the fourth, isn't that the same as saying I squared times I squared? Well, what does I squared equal? -1. And what's the second I squared equal? -1. So what is I to the fourth? Just a 1. Okay, there is a pattern here. I don't want you to memorize a pattern. But your answer is either going to be I, the -1, -I, or a +1. So how do I break down this I to the fifth? Well, I don't know what I to the fourth is regularly. So what I want to do is I want to break it into what I know. I can write this as I squared times I squared times I to the what? First. I want to break that number down into powers of 2 and 1 power of 1. Anytime I have an odd power, I'm going to have that extra I. So isn't this the same as -1 times -1 times I, which gives me +I. Okay, guys, here's the deal. I don't want to have to write out I squared a bunch of times. So think about I to the 6th. Can I write this as I to the 2nd to a power? What's the rule when you have a power to a power? You multiply. So 2 times what would give me 6? 3. Okay, so if you think about this, why did I pick I squared? Because I squared is the same as what? What does I squared equal? -1. And what's -1 to the 3rd? That's easy. Negative times a negative times a negative would? Every 2 cancel, so when I keep a negative and then a 1. Okay, can I write I to the 7th as I squared to a power? 2 times what would give me 7? 3.5. We don't want that, right? So anytime I have an odd power, I'm going to rewrite it as I to the 2nd to the 3rd times an extra I. All right, why did I do that? I'm going to rewrite I to the 7th with an even power and then the odd I. If it's an odd number, I'm going to odd I. If it's an odd power, I'm going to have I in my answer. So we already know that this is going to be -1 to the 3rd times I. Well, -1 to the 3rd would stay in -1, keep the I. Or I could just write it as -I. All right, let's add one more on to this. Well, 2 more. If I have I to the 8th, can I rewrite that with an even power? So I to the 8th, I'm going to write it with a base of I to the 2nd. What can I multiply that by? I to the 2nd to the 4th. Okay, every time I have a power, I want to write it in base of I squared, because what is I squared? What's I squared? -1. And then what's -1 to the 4th? Isn't that going to be a positive 1? Okay, now if I jump to the next one, I to the 9th, can I write I the 9th with a base of 2? No, I have an odd I. So I'm going to focus on this as I to the 8th times I to the 1st. Now, rewrite that I to the 8th as I to the 2nd to the 4th. So I always want I squared because I know I squared is -1. And I'm going to have that odd I on the outside. So, again, this is -1 to the 4th times I. What's -1 to the 4th? +1 times I would be I. Okay, we will come back and revisit this, but we might be revisiting with I to the 36 and I to the 37. So anytime you have this, you want to break it down to a base of 2 with a power that gives me 8. If I have an odd I, I'm going to have that I on the answer. So anytime you have a power that's odd, you're going to have an I in your answer and determine if it's positive or negative. Anytime you have an even power, the I is going to cancel out and give you a 1 or a -1. So it's not something to memorize, it's a tool to use. All right, now change gears. What operation am I asking you to do in these couple examples? I'm asking you to add or subtract. The problem is we see the parentheses and we just want to FOIL. We're not foiling, okay? So when you go to add or subtract, I'm allowed to have I in my answer, and I actually want I in my answer. So I don't want the square root of a negative. So there's an addition sign here. There's nothing to distribute. I'm just going to add like terms. -2 and +3 is 1. And then my i's, 4i and a -11i is what? Positive or negative? Negative, and it'd be 7i. So again, you're treating I just like you would treat x. But I has meaning. It's the square root of -1. Now, what's different about b? I'm asking you to subtract. So I would be using the distributive property. And if you want to rewrite it, it'd be 4 minus I, and then -5, and then -8i. I choose not to rewrite it. I choose to do addition of the opposite, but make sure you change every sign. Either way you cut it, 4 and -5 is -1, and then the -I and the -8i, that's like a -1i minus 8i, -9i. All right, you do the next two, please. Okay, check to see if there's anything to distribute. When I go to add the a's, the real term, they cancel out to 0, but when I go to add the imaginary part, it also cancels out to 0. So do you agree? 0? Okay. And part D, please distribute your negative sign. Make sure everything gets a sign change. A 10 and a negative 10 also cancels out. So 3i and 4i is 7i. This is called a purely imaginary number, okay, where these are all complex numbers because we've got the real and the imaginary. All right, next part. We're going to multiply numbers by using the distributive property and treating the imaginary parts as like terms. You will need to simplify any radical answer. So if we have an I squared, we need to change it to a -1. All right, so first things first, I'm just distributing here. Not adding or subtracting, distributing the 2i. So 2 times 3 is 6, keep the I. But 2 times -5 is -10, but it's I what? Squared. Now, typically, if it was x squared, we would leave it, but it's I squared, so we can't. What does I squared represent? -1. So isn't this like -10 times -1? It's multiplication, right? -10 times I squared. So I really have 6i plus 10 because this multiplies together. Technically, complex form, 6 plus or 10 plus 6i. Okay, so that was just distributing. Now in part B, I have a binomial times a binomial, so I'm going to want to, what's the acronym we use? FOIL. So first times first, 20. Outside, remember, foiling is just an organized method to distribute the 5 to everything, and then come back and distribute the -6i to the inner and last. So -24i and a positive 18, but don't miss the I what? Squared. Okay, so when you go to clean that up, what are your like terms? Yep, so I've got my 20, I've got a -15i and a -24i, so we should get -39i. But what about this? It's really positive 18 times -1. So instead of having plus 18i squared, we're going to have minus 18. All right, so that means we still need to clean up our real numbers or our constants, which would be positive 2 minus 39i. So anytime you get an I squared, you want to convert that to -1, and we're multiplying. All right, you go ahead and try C and D, and we'll talk quickly about them and go to E. All right, so I went ahead and did these. I foiled, I added the like terms, and they actually canceled out because this is a difference of squares, right? 1 plus, 1 minus, same numbers here. And then I had that minus 4i squared, which is really a -4 times -1, and final answer of 53. So I want to point out that the i's cancel themselves out here because the i's canceled and the I squared is -1. And so we're going to use this idea in a little bit. Okay, 36 was just 36i squared. Again, I squared is -1. Final answer, -36. So you never leave the square root of a negative. You replace it with I. But you never leave I squared because it simplifies to -1. If you have a higher power, you should never have a higher power of I other than I to the first. So any higher powers we're going to break down. Now, part E, I want to remind you that you can't distribute a power over addition and subtraction. So you have to write this as 2 plus 5i times 2 plus 5i. So if you quickly just try to square each term, you're missing the outer and inner or that middle part. This is a perfect square binomial. So we FOIL it just the same. For the outside is going to be a positive 10i, the inside's a positive 10i, and last is 25, but don't forget it's I squared. All right, I'll keep my 4. I'll add my like terms to get 20, keep the I, and this is going to end up being a -25 because it's 25 times -1. And then I'm going to put my like terms together, and that is going to be -21 plus 20i. Okay, good. Now there's a shortcut. You could square the first, square the last, and then double the product. 10i doubled is 20i, and then you clean up your I squared. Okay, here are those higher powers I was just talking about, right? So how do I simplify this -3i to the 12th? Any thoughts? Well, the first idea is I want to remember that I is always equal to the square root of negative 1, so we want to leave the I, but if I get I squared, I'm always going to replace it with a negative 1. This negative 3 is going to come along for the ride, and we'll deal with it at the end. So keep that negative 3, but let's break down this I to the 12th. Make it a base of I squared. What power can I go on here? Power to power, you said multiply, so 2 times 6. So do you see that I rewrote I to the 12th with the base of I squared? Okay, so keep that going. Keep my negative 3. And I squared is negative 1, but to the power of 6. And what's negative 1 to the power of 6? Positive or negative 1? Positive 1, because 6 negative signs, they would all cancel. So I'm left with negative 3 times 1, which is negative 3. Final answer. Okay, I to the 25th. Well, when I go to start this, can I write that as I to the second to some power? No, because it's an odd. So anytime you have an odd power, you want to break the odd power off. So I am never worried about all the ways I can write 25. I could make that 20 and I can make that 5. I can make that 15 and 10. I just want to break off the odd I that's causing the issues. So now I can write I to the 24th as I to the second to the 12th times I to the first. Okay, so I to the second is the same as negative 1 to the power of 12 times I to the first. Well, what's negative 1 to the 12th? 1. The idea is if we make this an I squared, it's always going to be negative 1 to a power. If my power is even, I'm going to make it a positive 1, and it's going to be 1 times I or just I. So we're always breaking everything down basing on an I squared. So I'll say it again. If you have an odd power, you're going to have an odd I, which will stay in your answer. If you have an even power, you're going to be able to break that up and all the I's will cancel. And then if it's positive or negative, all is determined by the power that you have here. Okay, now, next idea, we're going to get into division. So we've added, we've subtracted, we've multiplied, and now we're going to divide. But we're actually not going to divide. We're never going to divide. We're going to have to work with this because there's really not much to divide. So recall the expressions in simplest form cannot have roots in the denominator. So 5 over the square root of 2, we rationalize it, right? We multiply by the square root of 2, top and bottom, and we rationalize the denominator. Well, if you think about it, this has a square root in the denominator, doesn't it? I is the square root of negative 1. So I can't have an I in the denominator. How do I get rid of that? So one of the things people want to do is say, well, just multiply it by I. Now, if I multiply just this by I, I'll get rid of the I here because it's 4I squared, but won't I still have a 2I here? So I'm going to use that idea of the complex conjugate. So remember I introduced this idea and I said we would use it later. The complex conjugate of A plus BI is what? It's a rule. It's very simple. The complex conjugate of A plus BI is A minus BI. Now, the other thing, if you ever see a bar over a complex number, that is saying find the complex conjugate of A plus BI, it equals A minus BI. So if you ever see a bar over it, it just means change the sign of the imaginary number. Well, why am I changing the sign of the imaginary number? So the numerator is fine, but the denominator can't have I in it. So what's the complex conjugate of 2 minus 4I? So the complex conjugate is 2 plus 4I. Got it? Now, what you do to the denominator isn't the rule. We have to do that same thing to the numerator. Just like when you rationalize the denominator here, we multiply the top and bottom by the square root of 2. So I'm going to multiply by 2 plus 4I. And I'm going to use parentheses because everything's getting multiplied. So we're actually not doing division. There's nothing to simplify yet. We're going to rationalize the denominator by getting rid of I. And guys, I is not even an irrational number. I is in the imaginary world. So we can't have I there and we can't have a square root there. Okay, so you're going to do two separate problems of foiling. You're going to foil the top, clean it up, and you're going to foil the bottom and clean it up. So I like to do the whole top and then clean it up. So that's going to be a 10, and it's going to be, I'll write it out, 20i plus 2i plus 4i squared. This is just my numerator. So then I'm going to come in and add like terms and deal with my positive 4 times negative 1. So this would be 10 and a negative 4, so I get 6 plus 22i. That's my numerator. Now, if you want to show more work, okay? I just want to do it in one step where I fixed up my I squared and I added like terms. The denominator, it doesn't just cancel out. 2 times 2 is 4. 2 times 4i is a positive 8i. The inside is a negative 8i. And then last is negative 16, but it's I squared. When I go to clean this up, these like terms cancel, and then negative 16i squared is negative 16 times negative 1. So I really have 4 plus 16, which ends up being 20. Now, don't walk away from this problem yet. Do you see that you have these three pieces? What do all three pieces divide by? They all divide by 2. So I should be left with 3 plus 11i all over 10. The other way that you might see this shown is they factor out the GCF like this, and that is why you can reduce that to right here, because they all have a common factor. So if you're comfortable, you have to be able to take it out of all three. Okay, so we are really using multiplication to help us and the idea of the complex conjugate. So the problem is not that there's I in the numerator. We want I. We don't want the square root of negative 1, but you can't have I in the denominator. What is the complex conjugate of negative 5 plus 6i? What changes to get the complex conjugate? Only the sign of the imaginary number. Negative 5 minus 6i. We want this to multiply out like a difference of squares where those middle terms cancel. All right, so you're going to do two foiling problems and clean them up. Show the work that you need to show, and don't lose any of your variables or signs, or i's and signs. So I have a habit of cleaning up my numerator. How do I get there? Negative. No. Should this be a positive 15? Yeah. All right. Hopefully you agree with me. And then it'd be minus 8i. All right. The denominator, when I go to FOIL, remember the denominator is not canceling out, but we're canceling out parts. That would be a positive 30i and then a negative 30i. And last would be a negative 36, but it's I squared. So that's going to cancel, and this will be negative 36 times negative 1, which is positive 36. Okay, so add those up, 61. And then before I'm done, I want to double check. 27 and 8 have no common factors. So even if this was like a number down here that canceled with 8, I can't reduce it from all three. So that is my final answer. Okay, what's different about the last one here? Example C. There's no like plus or minus. It's just the complex number is just the imaginary part, right? Okay, there's two ways of doing this. One, the rule is to multiply by the complex conjugate. So you would take that 8i. What's the complex conjugate of 8i? Negative 8i. Now, I don't want to do it this way. I can do this. And if I do this, the numbers get bigger and then I'm going to reduce it. The idea is if I have just this, I can actually multiply by just I. Now, if you understand this, it's a little bit of a shortcut. If you don't understand it, always use the complex conjugate and then you're just going to have to reduce it. Why can I just multiply by I? Because the denominator gives me 8i squared, which becomes negative 8. And the numerator would be 3i plus 7 times I squared, so negative 7 plus 3I. So if I have just one term in the denominator, I can get my I squared and get it out of there. Now, you might not see this answer. Most of the time, they would divide out the negative, and you would get 7 minus 3I over 8. Either answer is acceptable. Do you see that all the signs are the opposite? Now, if you do it this way, you would get the negative 24I, the minus 56, that's an I squared there, over negative 64I squared. Clean it up, and then do you see that you'd have to divide everything by 8, which was the extra 8 that was in there. So if I only have the imaginary part, I can simply multiply by I as a shortcut, but you understand I can't just multiply this by I because then I'd have a 2I, and I'm stuck. So I have to use the complex conjugate.